My favorite animation trick, exponential smoothing. I've had my eye on this post for a while. I love animation and getting nerdy about this stuff. Huge shout out to Osiris, hopefully I pronounced your name right, for writing this blog. Really excited to take a look. There's a certain simple animation thing that I've been using almost since I ever started doing anything related to graphics. I use it for rotating and moving the camera, for moving figures in a turn-based game, for moving UI elements, for smoothing volume changes in my audio library, everywhere. So I decided I'll write about it. The trick itself is nothing new. In fact, you've probably already heard about it or even used it, but I'll also show you in some examples, as well as explain how it works mathematically. Oh no, math. My worst fear is a JavaScript dev. This should be fun regardless though. Toggle buttons, everyone's favorite. Speaking of UI, say you're making some UI component, maybe a toggle button, something like this. And it immediately just switches states. Beautiful. This looks like something I'd write. It simply computes the position of the switch as a function of its state. Position X equals turned on, ternary, everyone's favorite. If it's turned on, then it's max X, otherwise it's the min X. So that's just the location that it's going to be put in. This works perfectly, but it feels a bit lifeless. Adding some animation to it would be cool. Animations are not just a fancy visual thing, they help the user understand what's going on. Instead of teleporting the toggle indicator to its new position, let's move it slowly. Already so much better. It's a nice little slide. Sure, this will look great at the 30 FPS all my videos are filmed at. The downside is that we need to run some updating animation code now. Position X gets the new value added. So if it's turned on, then it's 1 or -1 times speed times dt, which is why am I forgetting what dt stands for? Have I not done math for that long? Am I that dumb now? Delta time. Yeah, okay, delta time. So this is the amount of time that we want it to take. Thank you, chat, for making me feel less stupid. And then position X is clamped the position. So this is to make sure it doesn't go further than it's supposed to. However, this still looks a bit clumsy due to having a constant speed, which means that the position is a linear function of time. Let's add some easing function on top of that, like the classic cube. So this makes it so when it moves a little smoother. So it ramps up and down the speed. It's not a linear speed like here, or it just slides the exact same speed. So here's a basic cube ease. Makes it a little smoother, especially in the middle there, or the square root. That feels so much smoother already. The difference between these may be hard to see, so let's slow down the animation by a factor of 8. This sounds very handy. So here's the linear, cubic, and square root. So linear, oh, they all go at once. Yeah. It's actually really cool seeing how these compare when you move them that much slower. This time, instead of just updating the switch positions, we have to keep track of some extra animation state. So T is turned on 1 or -1 times speed times the delta time. T is clamped, and then the ease. So ease is us screwing with the actual change value that we want to use here. Ease is 3 times t minus 2 times t times t. Jesus Christ, this math shit's insane. Here I'm using the fact that smooth step is symmetric in the following sense. 1 minus function of time equals function 1 minus time, meaning that the forward and backward animations can use the same code. Clever. With square root, things are a bit different. We have to explicitly use a different easing function depending on the animation's direction. Also a fair point, once you're doing square roots, it can be annoying to do that math. Ease is turned on, will it square root, or will 1 minus square root 1 minus in order for it to work in the negative case. Whichever looks best is arguably a matter of taste, but of all these, square root is my favorite. The switch starts moving really fast because square root has an infinite derivation at 0, but then slows down nicely as it reaches the destination. The cubic one's my second favorite though. The downside of this version is that we need quite a lot of bookkeeping, even in the simplest possible case of a 2-state toggle button. Later in the article, I'll show how this becomes a nightmare in more complicated scenarios. Another downside is that it has a discontinuity. It jumps suddenly if the user clicks on it in the middle of an animation. Let's go back up and try that. So yeah, that jump right there, you see that? Oof. Yeah, it's brutal. I do like that it starts really fast because it feels more like it's reacting as you're clicking. Because as soon as you click, you see a lot of motion immediately, which feels really good. And then you have more time to process that it's getting to the end. Yeah, I like that a lot. I really like that it starts up fast. I think that's a nice touch that we're going to want to keep. So let's see how they handle the jumping problem. Oof, that is nice. What is this? This is exponential smoothing. That's at least what the author calls it, for reasons that will become clear later. I've also heard it being called approach, and I'm certain it has its own name in every engine. Here it is slowed down to 8x and compared to square root. Yeah, those are simple, but this is much slower at the end, and you see that extra in the 8x. But if you do that, like stopping it halfway, you can see how much less jank it is. That is a very nice change. Here's the code for the exponential version. Target equals state.value min or max. So this is the target where we want to go is the like max or minimum position. And now the x position is going to take target minus position.x times 1 minus exponential of the negative dt, which is the delta time for how much time you have left to change, times the speed. Interesting. Intuitively, on each frame, we nudge the current position towards its target position, which is determined by the on and off state. However, the amount of nudging, 1 minus the exponential negative dt times speed, looks really weird, doesn't it? Before we see where it comes from, let's have a look at some more complicated animations. Camera movement. Oh boy, I know way too much about camera movement shit. Yeah, like how cool is that? Just using an iPhone as a virtual camera. So you combine that with like a really cool filming setup and faking the whole thing with a real camera in quotes. Yeah, you can see how much more natural the camera motion looks like when you're using something like this. Just like a human's hand will always generate the right amount of shake compared to something fake. Yeah, you can see it here, how much more real it looks when they're using the phone camera to like do the camera shake and such. It makes these CGI things feel much more real. And there's a reason that even like the cinema world leans in this direction. Keep an eye out. You might be surprised how many things are using something like this for filming. The point I'm trying to make is that camera movement is hilariously hard, and our solution is usually a human carrying a fake camera with motion tracking. So I'm curious how they're going to use this for camera movement. Say we have some kind of map and a camera that scrolls and moves around. Here is a map, and you can click, and it's pixel by pixel, swapping things around. Not great, but for a Minecraft map viewer, I suppose this makes sense. Yes, I've made a whole procedural map generator and renderer just for this example, and I have zero regrets. That's some chaos. To make something like this just for a blog post about animation is beautiful, and I appreciate the author immensely for it. Again, this begs us to add some animation. Let's interpolate it with a constant speed. That feels pretty jank. It just, stop. Like, it's the stuttering. Hopefully that's not something that's like broken. I'll refresh just to see if... Yeah, it keeps doing that after you do one movement. It gets all jank. Hopefully that won't happen in the rest of the examples. Here's the code. Position x equals sine target.x minus position.x times speed times the delta time. The same with y. So we're just making sure that this is a positive value, and then we're moving it the right amount. Cool. See the jittering? Oh, wait, no, that was actually intentional. See the jittering after the animation completes? That's because target x minus position x keeps alternating between being positive and negative. Instead of sine delta, we need some function that clamps. So here's our clamp. It has a min and a max, value plus equals delta, update position x, target x, speed, update. Cool. Quite a mouthful for such a simple thing. There, now it actually works as expected. Still jank, but at least it doesn't do the weird locking up. That is definitely a lot of code for something this simple. Much better, although it's still a bit clumsy and also weird if we move the camera faster than the animation completes. Let's try that. Yeah, that is awkward. We could, as before, add some easing function like the cubic one. Let's see how that looks. Already so much better. But if you press it a bunch of times, it's still kind of jank. Although this time it gets complicated. We have to maintain a queue of requested movement events and animate them one by one. Otherwise, I have no idea how to slap the easing function here. This still looks a bit weird when moving the camera fast enough. We could just ignore the user's input while the animation is active. But this is a deadly sin, as it is infuriatingly frustrating from the user's perspective. Absolutely agree. Because if you click this twice, and one of the times it's still animating and it only moves once, whew, that is the most annoying thing in the world, especially if like the third click is just barely after. So you get 2 of the 3 clicks. Yeah. Canceling user behaviors while an animation is running can be very, very annoying. So what's the perfect solution? Why, exponential smoothing, of course. The code barely changes compared to the toggle button example. Position.x plus equals the target x, position x. Yep. It's actually nice and simple, especially when you compare it to the mess that was here with custom update logic, with clamping and everything. Just using the target position and the amount of time that you're intending for this to take as the core of how you reposition, really handy. Good stuff. And here's how it looks. Let's stress test this. First off, just like the one little slides like that look great. If I click it a bunch, this is really nice. Pretty nice if you ask me. Notice how it speeds up naturally if you click fast enough. How fast can I click? Too fast. Need a mouse if I really want to test this. But it does look fantastic overall. So let's take a look under the hood. So what's up with this 1 minus exp? Am I wrong about this being exponent? Let's see what it is. What on earth is it though? Let's start with a simplified version. We have some animation. It has a current position and the new position target, which it must move towards with some speed. To make the movement faster when the difference between position and target is large, we make the speed proportional to the difference. Position plus equals target minus position times speed times the delta. Notice how it doesn't require maintaining any state other than the current and the target position. That is really nice too. That is really handy. And it's probably one of the big reasons why I like this a lot. Almost all the other solutions require you maintain some other type of state to know how fast you should be moving and like where you're at within the animation. Since animation is based entirely on the planned position and the current position, you don't need any other data. And my inner functional programming nerd is just screaming with joy as they realize how much simpler this is to manage your state for. Also, if you're accelerating something like your graphics card, not having to rely on storing additional data when you might not even have memory, especially when you have potentially millions of these elements around, makes these solutions much more scalable as well. It doesn't even need to keep track of the time that's elapsed since the start of the animation. It automatically adjusts if the target suddenly changes. Super, super handy because everything's based on how close these are rather than how much time has passed. Now, this already works perfectly in many situations, but there's a small catch. Here's the toggle button again with the above update code. Update. We all make mistakes. I totally understand. I know I've made much worse typos and most of our editors don't have spell check. And even if they did, they'd be getting a lot of these things wrong. Pretty impressive we're this far in. This is the first typo though. So A+ to the author. Oof. Yeah, that was jank. See the jittering? That's because I've set speed value so high that speed times dt became larger than 1. Specifically, if I use speed as 220 and dt is 1 over 125. That makes sense. If your speed goes higher than 1, then you can like break out of the box. You saw that it just barely was visible. But you saw the part where it like goes too far and is jank there. Makes sense. To understand what's happening, it's useful to rewrite the code above using LERP. What the fuck's LERP? It's a methodology of curve fitting in math. Oh, it's just linear interpolation. Okay. I didn't know the phrase for that, or the shorthand for that. Yeah, it's linear interpolation. That makes more sense. You can check this is ultimately the same formula. We can clearly see what's going on. The formula interpolates between the current values and the target value. The closer the interpolation parameter, which is speed times dt, is to 0, the slower the interpolation. The closer it is to 1, the faster the movement. So what happens when the value is larger than 1 is that it overshoots. The only reason it still works is that speed times dt is less than 2, so that the absolute delta between position and target still decreases with time. Here's an example where it's less than 2. Oof. And then here's one with speed greater than 2. So that just leaves the page entirely. That doesn't do anything useful at all. To solve this, we could simply clamp the value by 1. So min is 1 speed times dt. However, this doesn't seem like the right thing to do in all scenarios. Consider why speed times the delta might actually happen to be so large. One reason that your speed might be too large is that you want a quick animation. However, as we've seen with the above toggles, this is actually way too quick for any reasonable user. The actual animation is impossible to notice, so our speed value is usually not that high. The other reason is that the delta time is too large. This is the time between every update. And if this is too big, then the update is going to feel weird. Maybe because your code runs too slow and your frame rate is dropping. Maybe because the user moved to a different tab or window and your code was sleeping and now it got woken up with a DT of many seconds. This is another important thing. If you're building these complex animations and you have them running in other tabs, it's a good idea to change the behavior so they're less CPU intensive when things aren't in the focus tab. This is very common. If you look at something like Discord and you have like a GIF that's playing and you open up another window, but your Discord is still visible, if it's not focused, it will pause all the animations to save CPU. When applying such a delta time to something like physics, you certainly want to clamp it, or subdivide it into several updates or more. With animations, however, wouldn't it be cool if everything worked perfectly, even in this case? Even if your physics might lag, at least the camera and buttons would still work nicely. As a user, I'd really appreciate such care. This is a very interesting proposal here, the idea of it just working even in laggy cases. I'm very curious how they solve this. Oh god, I'm suddenly a lot less excited. I don't want to do differential equations, but we'll see where they bring us. Okay, we want to solve the problem, but how? Here's the two-step recipe. First, we have to realize that what we were doing is numerically solving a certain differential equation, and then we have to solve the equation symbolically and then use the results directly. Time-dependent updates that work for a small delta time but break for large delta times are pretty typical for numerical solvers of differential equations. Oh boy. What equation does position plus equals target minus position times speed times delta solve? Wherever you see a plus equals b times dt, this corresponds to an equation. Delta over delta time a equals b. In our case, the equation is the delta times position equals target minus position times speed. I will die if I keep typing these formulas with all the words spelled out, so let's make a few variable changes. Call x equals position, a equals target, and c equals speed. I appreciated typing out the whole thing, but I understand. Cool. So x is position, a is target, c is speed. So this times x is the same as a minus x times c. Solving this just needs a few simple tricks. No. Call it simple. My brain doesn't work this way anymore. The output here I kind of get, which is that x is x of 0. When does x0 become a thing? It's a new derived value. Does it not describe where that came from here? Okay. I'm not going to pretend that I'm smart. Oh, x0 is a starting point. Okay, that makes sense. Okay. So x minus a, where a is the target. So x minus a is the total distance to travel. And that distance should be equal to the starting point minus a times the exponential of the negative c, which is speed times time. Is that all right? Cool, I did. And if we simplify it further, then x is the starting point of x plus a minus the starting point of x times 1 minus the exponential of negative speed times time. Weird, but this math, I guess, checks out. I'm sure somebody smarter would have called this out. Otherwise, my brain hurts. Let's keep going. Apparently, a similar exponent appears in volumetric rendering for similar reasons. Interesting. This is why I write JavaScript. It's not important to understand exactly where this all comes from. The point is that if we believe that position plus equals target minus position times speed times delta is the right formula for a small dt, then position plus this times 1 minus exponential of negative speed dt is the right formula to use for any dt, because this effectively cancels out to be this for the small numbers, and this forces the speed delta that is actually changing to be a reasonable value by clamping with the 1 minus exponential call here, forcing it to fit always. This is further supported by expanding the latter equation in terms of Taylor series for the exponent. So exponential of x is roughly equal to 1 plus x. So this longer thing is basically the same equation. My brain hurts. I'm not paid enough for this shit. The cool thing is that it doesn't care about old values. If you have your previous value of the starting point of x, and you know how much time has passed between the previous and the current iteration, you can compute the new value. This is a direct consequence of being a first order differential equation. So TLDR is that position plus equals target minus position, this whole guy, is the right formula to work for any speed as well as delta time. Even if the product of speed and delta time is too large, this will handle it nicely. Since the exponential of a large negative number is just something close to 0, so 1 minus that will be close to 1. Good shit. We can, as before, rewrite this using linear interpolation. I'm not going to read this part. The article's in the description if you want to dig deeper into this math stuff, because I'm too dumb for it. I want to learn about choosing the actual speed, though. Usually we think of animations in terms of their duration, like the toggle button should move to the new place in 0.125 seconds, which is the actual value used in the examples in the beginning of the post. After that, it should stop moving. With the exponential formula, however, the animation technically takes an infinite amount of time to complete. We kind of saw that if we go back to the first exponential. See, it's still going a little bit. And it just goes technically forever because it never quite approaches the limit where it hits the end there. So yeah, it never quite equals 0, which means that the position and the target never actually hit the same number. Since you have a limited number of bits to store all of your float values, they will actually get to the same value, but the amount of time is insane and hard to know for sure. However, in practice, we have a ton of limitations. Yeah, look at that, they're going to call it out. Position is floating point, it quickly reaches the precision limit, and it becomes equal to target in practice. If it's the camera position, though, the user probably won't even notice that the animation is still going, since the difference between these two values is so small, even before it hits floating point precision limits. One more fun tangent. Slight spoiler for Outer Wilds, but if you haven't played this game already, play this game. Please play this game. If you're into video games at all, play this. The less you know going in, the better. I almost want to say skip this part, but it's not too big a deal. The way the world works, I don't necessarily want to play the exact clip where they talk about it, but I want to showcase a bit of like the game's world. So the map for Outer Wilds is pretty big, and the whole game has a physics simulation that is keeping everything in this universe, like physics and science-wise, as close to accurate and simulated as possible. But when they have all of that running, all with the traditional like Unity grid system, and you fly too far to the edges, when the number for your position gets really big, you run out of precision points. So if I have like my position for a character, so cost camera position equals X 12, Y 201. Nothing suspicious here. But if we have a limit of like, let's say 8 digits, 1, 2, 3, 4, 5, 6, and here we only have 1, 2, 3, 4, 5, This little bit of decimal stuff helps a lot with camera movement. So if I want to move the camera X plus 10, and I have all of the wiggle room here that I can have different positions as I get there. So I can have like 12, 2, 6, 4, 5, 1, 12.5, whatever. And each of those is incrementally moving it so the camera can move smoothly. What happens if we have a much larger number in the front? Then we only have a couple digits of precision for the decimal. In fact, in this case, we've went from having 6 digits to 2, which means that your camera movement starts to get jank. If you get far enough where you don't have those precision points at all, or you get so far that it just zeroes out like whole value points, now your camera is moving in whole numbers or even like tens or hundreds, which can make the camera movement really jank, similar to what we saw in some of the earlier examples. This is a disaster when you're making a game. The way most game devs work around this is they have limits for how far you can go in X and Y coordinates before they swap the map out. So you can never go more than like 2,000 in any given direction. The way Outer Wilds solves this is these values are actually set to always be 0, 0. And instead of you moving where your coordinates change, whenever you do something, they apply an opposite force to the entire game universe and move the universe around you in order to make sure the camera never gets jank. Mind-boggling, insane shit. But that's the things that we do to deal with the fact that floating point as a method for managing your camera can get real messy real fast. The number of bits you have in your numbers matter a hell of a lot more as a game dev than they do for almost any other field in software engineering. Just insane shit. And if you haven't played the game, go play it. And once you've played it, go watch this documentary by NoClip if you want to learn more about how and why they made these types of decisions. It's insane. So yeah, back to what they were saying about floating points. So what does the speed parameter even mean? It means the following. 1 over speed is the same time in which position becomes closer to target by a factor of e... Oh God, everyone's favorite. Do what you want with this info. I usually set speed to something in the range of 5 to 50. For a linear or cubic animation of a certain speed, I usually set the exponential version to be 2 times the speed, which feels about right. Again, this is what was used for the examples above. So, exponential smoothing. If you Google exponential smoothing or exponential moving average, you might find the wiki article on something that's completely unrelated, which, nevertheless, features some pretty similar formulas. It actually is the discrete analog of what we were talking about in this post. Interesting. It's for time series data using an exponential window function. That's funny that this other definition for it is just for math. Maybe they're stealing this term because I think it fits really well here. Suppose our delta time is always the same. Also suppose that target changes as often as every iteration. Interesting, so the place we're going is changing constantly. Then, indexing the values with the iteration number, we compute something like this position I is target I, position I minus 1 times factor, where factor is 1 minus the exponential, cool, our little helper for clamping the speed. In this case, one typically sets factor directly to some value between 0 and 1, instead of deriving it from other values, although the aforementioned wiki article does explain what this factor actually means. People use it in signal processing for the same reasons I do for animations. It doesn't require maintaining previous values or any other obscure state. This makes a lot of sense for dealing with like crazy data processing. If you have to deal with additional state for every piece of data you're processing, that falls apart fast. But by using this formula, you just need the intended position and the current position. You've handled everything you need. Good stuff. They also use this in digital audio, where you typically have a fixed delta time of 1 over the frequency, which is the inverse sampling frequency. Good old 4410 and 48. My inner audio engineer is scared that I should know more about this now. Yeah. Love this. Last paragraph title. I had the idea of this post for many months. Glad to finally get it done. As usual, watch my devlogs. Fantastic. Of course, they're a game dev. Nothing has been less surprising throughout this. Huge shout out to Nikita for this awesome blog post. I'm immediately subscribing to their channel. I recommend you do it as well. Subscribe button's right there. I'll be sure this is linked in the description. Yeah, thanks for reading. Thanks for writing this. This was awesome. I like animation, game engines, and all this stuff a lot. I'm curious how you guys feel about it. This is different from what I normally cover, but it's a really, really good post. And I would love for you guys to let me know if you want to see more like this in the future. And until then, peace nerds.